4 years ago on his studies. Other people who are interested in periodic structures are Professor Amnon Yariv. He's a former student at Poitiers, and his colleague Emmanuel Marom, who studied Bragg optical fibers. These are structures where have periodic, again, the electric layers, concentric layers. And they wrote a paper in 1978. And 2 years ago, in 2009, Amnon Yariv gave here one of the plenary talks, and Emmanuel Marom got the award, was one of the 4 scientists who got the award for scientific research. And I think that with this background, Professor Russell, I think, got the inspiration. He has been interested for many, many years in the propagation of light in periodic structures, and he then developed holy fibers from holes, and he coined the term photonic crystal fibers, which he invented and made great impact on science and technology. And yesterday you heard in the lecture of Professor Hensch that he also mentioned photonic crystal fibers as part of his research. Professor Russell was in Southampton and then in Bath. Now he is a director of a Max Planck Institute in Germany, and he dedicates, I guess, most of his time on photonic crystal fibers, and he'll tell us about his recent research.
Okay, I think I'm all set. So thank you, first of all, to the organizers, in particular Zev Zalewski, for inviting me here. This is a great honor. On my first visit to Israel, I get to give a talk like this. I'm wearing a tie. I apologize for that to all the physicists present, because I don't normally do that, I have to say. Most of my students see me with a tie, they don't recognize me. And I'm at a newly formed Max Planck Institute in Germany. This is one you might not have heard of before, and it's actually very appropriate. It's the Max Planck Institute for the Science of Light, in English. In German, it's the Wissenschaft des Lichtes. They didn't like the idea of well, they don't really have a word for science, you see, but if we said Max Planck Institute for Light, then we have all that stuff that Professor Katzir mentioned yesterday, which we did not want to be associated with. We want to be just on the science of light, not the other stuff. So, interesting. So that's we're only around 2 years, so we started at the beginning of 2009, and we're still building up. A little bit of background about the Institute itself. So, Photonic Crystal Fibers, Keeping Matter in Focus, a subtitle. I'm going to talk mainly about the hollow core photonic crystal fiber. This is I don't want this to be too loud, so I'll try and keep away. Okay, but just by way of very simple introduction for anyone in the audience, and I'm sure there's almost no one, but just in case there's someone in the audience who doesn't know what a fiber is, the most common kind of fiber that you find, of course, in the laboratory and in telecommunications is the so-called step index fiber, where there is a core in the center which has a refractive index that is a little bit higher than the cladding, and as a result you can trap light in that core by a very well-known process of total internal reflection. If we take a little more of a look at how this works, this is the cross-section of the fiber and the side view, and the index difference is really very tiny between the core and the cladding. It's only less than 1% in some cases, and in this case I've shown 2%. And the idea is that the rays of light bounce to and fro, and are confined by total internal reflection, of course, and only certain specific angles, at only certain specific angles, does one obtain a mode, of course. You can't just choose any angle you like, you have to choose certain angles that provide a proper guided mode in the core. Now, this idea dates back, of course, to Charles Kao, who was mentioned of all sorts of famous people yesterday. Charlie Kao was perhaps not quite so famous as some of the names that Ted Hensch mentioned yesterday, but nevertheless he was the first person to suggest seriously that one could use this technique or this mechanism for optical communications. And I think at the time people laughed at him, they thought he was crazy. Truly, everyone was working with microwaves, and they thought, why would we want to work with light? How could you do this? And so, quite remarkable, I think, that he persevered. And now we have the whole telecommunications revolution using light, of course. So hopping a little bit more recently, this is one of the solid core photonic crystal fibers, or PCF we call them, which we first made in 1996. This looks a little bit like the step index fiber. It has a core which is solid glass, but it's surrounded by the same material, except that material is permeated with a two-dimensional array of hollow channels. As a result, you could say, well, the average refractive index around the core is lower, so therefore total internal reflection works. On the other hand, that's a periodic structure. It has all the properties of a periodic structure, stop bands, band gaps maybe, interesting sorts of dispersion. And in fact, this fiber doesn't just trap light by sort of total internal reflection, whatever that may, but it also, there's mixed in with it is photonic band gap effects. This isn't so widely understood actually, but it is actually true. And this is the reason why it gives such remarkable types of behavior there. In fact, the small core version of this particular fiber was used by Ranke and co-workers, as Ted Hensch mentioned yesterday, to produce supercontinuum. And that's been a real revolution in light sources, as we all know. I imagine there's no experimentalist in the room who doesn't have a supercontinuum source of some kind in the lab if they work with light. The more revolutionary version of these fibers is the hollow core. The concept of this dated right back to the beginning, very shortly after the proposal by, it was mainly Eli Yablonovich, I have to say, who inspired me, I think, with the concept of the photonic band gap. We had done all sorts of work on propagation in two-dimensional periodic structures long before that, but he came along with the concept of the photonic band gap, the idea that maybe you could do that. What a nice question to ask. What a difficult one to answer, in fact, in practice. So I was working with fibers, and I thought, well, maybe we could create a two-dimensional photonic band gap much more easily than you can in 3 dimensions. Turned out to be true. In fact, it took us 7 years, in fact, to make the first one that worked. But the idea here is to trap light in a hollow core. Why is that interesting? Well, let me just answer the question. What might that be useful for? Why would you want to bother making such a thing? Nice that we've already heard of Lord Rayleigh or John Strutt. There he is on a postage stamp from Granada. Very nice moustache. He was very creative, actually. And of course, he worked all the stuff out about lenses, amongst many other things. In particular, the depth of focus of a lens, which of course scales with the strength of the lens, how strongly it focuses. And in fact, the spot size and the depth of focus are related to one another. So that if you, say, wanted to maximize the product of intensity and interaction length, which you would like to do often in nonlinear optics, that product actually turns out to be proportional to 1/wavelength in this particular case, at least for a Gaussian beam. Interesting, you can throw away the lens and you get the same product of intensity and interaction length. The only thing that happens is that your device gets very long, of course. So in practical terms, it's good to use a lens if you want to get this product as high as possible, but actually the mathematics shows you that you don't need the lens. So this means that you can only keep a high intensity over a relatively short length, which is not always what you want to do. You'd like to be able to keep a tight focus on light over long distances. This is what the hollow core photonic crystal fiber with the two-dimensional photonic band gap allows you to do. It allows you to take that product of intensity and interaction length and make it, you can work it out, it's going to be proportional, the intensity proportional to 1/radius of the core, of the hollow core squared, of course. And the interaction length then goes simply as 1/loss, and the loss per meter can be very small. So we have a product that can be huge. In fact, it can be 10 million times higher than in the focus of a lens, or 10 million times higher than for a Gaussian beam. Now, given that factors of 10 billion don't crop up all that often, especially in applied science, it's not surprising, perhaps, that this particular structure, simple as the concept is having a major impact in various areas of, in particular, gas laser interactions, and some other areas too. So I thought I'd talk mainly about these applications. Let's have a look and just look in more detail as to why this hollow core photonic crystal fiber is interesting. Well, what it does essentially, it eliminates diffraction in empty space. If you can view the core as empty space, it's not quite, of course, but nevertheless, there's nothing in there. If you evacuate it, there would be nothing in there, and the light would simply feel a little bit of glass on the edges. More than 99% of the light is actually in empty space. So you've eliminated diffraction of light in empty space or in vacuum. and the light is trapped in a single transverse mode, which means the intensity profile is highly reproducible, which is very advantageous